of 20 students have gone.
Oh,
That entire group of 5 people is gone. So yes.
Okay, yeah.
The USC crowd?
Yeah.
Yeah, there was a lot.
Yeah, they're all gone basically, so that is...
But he was going to give a talk this afternoon, but now it's on, right, the schedule changed.
Yeah. He had to cancel last minute.
Yeah.
Okay.
C'est pas les mêmes logos.
So that, how many people believe that these logo are ugly and too complicated? Which one? I mean, you have some redundancy, so it's not even clear.
It's very French as a style of logo. So this is your school.
Oh.
This is your institute, this is your AI institute,
But
and the
I really
institute
want-
is part of the AI institute, so it does make sense.
Oh my God, I just realized that.
Yeah, it's all you can see from that.
Yeah, but
Discussion
in some sense, it's kind of self-explanatory to some extent, right? Like, I mean, I think we should put in all logos, I mean, because we have a French system which is pyramidal, I think you should just aggregate all logos. Whenever you do a matching between institutes, you just like the logo is the aggregate, and simplifies things out.
Yeah.
I think we'll start. So, is this on? I think, okay. So thanks everyone for coming after the lunch break. I think there are some people finishing up some conversations who will also enter in a few minutes, but we're very fortunate to have Professor Aymeric Dieuleveut from École Polytechnique and the other 2 institutes, which we just talked about also. I think it's going to be a very different talk from a lot of the talks, maybe because Aymeric's going to tell us about computer-assisted proofs and maybe potentially how that changes a lot of how we think about optimization analysis. And without taking more time, let's hear from Aymeric.
Yeah, I don't know if this is on. I guess you can hear me. I have a loud voice in any case. Thanks for the introduction. Thanks for setting up all the workshop. We have the honors of doing the last talk. So I'm in charge of saying, congratulating the organizers for all this great week. As you have just said, I'm going to talk about something slightly different. I'm going to talk about optimization. And I'm going to try to explain how maybe computer-assisted proofs can help us to some extent and in particular setups. So I'm going to start by an introduction, which is a bit, I would say, a more broadly context of things that have happened at the intersection between proofs and optimizations and AI. I think the first point is that there is excitement about LLM for mathematical proofs. This is partly due to Sebastian's, not Sebastian Stitch, Sebastian Bubeck, the French Sebastian, that last year during the summer gave a tweet saying that GPT-5 had just advanced the state of knowledge in mathematics and made a new proof. And this was actually true. GPT-5 was able to improve on the first version of an archive paper, although the proof that it gave was worse than what was in the second version of the archive paper, which was already released. But I mean, that sparked the debate, and since then we have seen many of those posts advertising for like, okay, proofs obtained thanks to LLMs. So this was interesting, and it actually echoes with the fact that optimization, first-order optimization in particular, is maybe one of the easiest science to tackle with LLMs because it has a lot of structure, and maybe part of it can be improved with LLM techniques or generative techniques more generally. So I'm going to talk about computer-assisted proofs. I'm not going to talk about LLMs, but the two things are connected. And in particular, the proof that the LLM had provided here was actually based on the same exact set of tools as the ones I'm going to talk about afterwards. That's the first bit of context. The second bit of context is federated learning. I have removed the slide on federated learning from my deck of slides because you all know what federated learning is. I'm just going to give a couple of thoughts and beliefs or feelings about federated learning. The first one is that it's actually fantastic because it gives us, as people that like to do theory or methodology and algorithms, a chance to have an actual problem to work on. So trying to incorporate constraints from societal, privacy, legal aspects, efficiency into algorithms is actually fun and probably meaningful and probably something not easy to do, proved by the fact that we have spent a week talking about difficult things in federated learning. The second bit about federated learning is that it's extremely active. So there are on average about 30 papers per day that refer to the original FL paper from 10 years ago. That's a lot. We cannot process that much content. Not all of those papers are related to optimization. Many are, and I mean, this is something that we can say like that, or we can say like what Zachary did on Monday, that federated optimization is an enormous well to draw from, and I think this was actually a very fair statement. The complementary bit of context of that is that the typical average paper in federated optimization is typically not easy to read, so maybe I can zoom in a little bit here, but that's not going to help you much, because this is a long list of equations, right? And this, obviously, I'm not pointing the finger at anyone. This is one of my own paper, and I wouldn't do that. But it's true. I mean, we typically have to do proofs that are technical to some extent, and this is reasonable because, again, we maybe learn things from this. Nevertheless, this is very hard to proof check. There might be mistakes. The rate that I get at the end of these 20 pages or 50 pages of proof is not always the tightest one. So those create many challenges. Like we have some kind of limited trust in what we can obtain from federated optimization guarantees. I mean, either the proof might sometimes be not verified, and maybe I can be a bit provocative on that, but I don't think most papers submitted at NRIPS or the conferences, the proofs are properly checked by reviewers. I mean, those reviewing at ICML, raise your hands, and I'll ask you the question of how much you check the proofs. And so even if the proof is correct, the rate might not be tight. So we end up comparing methods based on upper bounds that are not necessarily the correct ones. Okay, so that's the second bit of context. And I'm going to even here stop for a minute and do a step back, which is to a question that I've asked to several of you, which is like, why do we even want to do theory in general and theory of federated optimization? And I think the first answer is that theoreticians believe theory helps. And I think that's a very fair answer. And I think that's actually true. And there are trade-offs here. We have talked about those trade-offs in previous talks. I think one of the trade-offs is that typically the rates that you obtain are not necessarily, reflective of the behaviors in practice. They're not necessarily meant to be reflective, but they are not always reflective. That's a challenge. But despite that, there are plenty of good reasons to the theory. And this is an aggregate of some of the conversations I had with some of you during the week, and I agree with all of those points. Understanding is always good, and to some extent, even if the rate is not something that really makes sense at the beginning, it can help, and maybe it helps for tuning, maybe it helps us confront and build our own abstraction of what algorithms are doing. And as mathematicians, building abstraction is what we, strive to do. And maybe sometimes we come up with new schemes, inventing thanks to the theory. Maybe sometimes we understand the limits of schemes that were invented by practitioners. And maybe sometimes we need a certificate from a legal aspect. And at the end of the day, we have to start somewhere. So I do believe in theory. And I'm going to say that the next statement is, if we believe in theory, then we should try to have the most relevant theory. And this is perhaps something that we can debate a bit more. And I'm going to say that to have a relevant theory, we need basically two blocks. The first block is a good model of practical setups. So a good model means good assumptions on the regularity of functions, on heterogeneity, and discussing about how we model heterogeneity has been one of the big topics of the week, and on the communication model. And then once we have a model, we need a precise, a tight, and exact, whatever you want, the best possible analyses under that model of the behavior of our algorithm. And for me, this is two parts of the world. The first part of the world is the fun. This is like trying to actually, this is Sebastian talking about delta similarity, and this is actually interesting, trying to find the best, the best ways to describe heterogeneity has been something that we're excited about, right? Because, oh wait, is that going on the slides that you do next time? So it's interesting, right? We want to, it's our modeling work, trying to find the good ways to describe heterogeneity and what relevant assumptions are. And the other part is what I call the burden, right? The burden is doing those crazy proofs that take a lot of time to verify, to write down, etc., etc. So when we have these two things in mind, basically my goal, and the goal of what I'm going to present afterwards, is to make step 2 almost automatic. So my promise, to some extent, is that I can make parts, in some situations of steps 2, something that we don't have to deal as much with. We can, automate it some parts, have a verification of the proof that is partially automatic, maybe even not do the proofs, and maybe at the end of the day, rely on what I'm going to call empirical laws. So for one of the rates I get that I'm not even going to show, I'm able to give you a formula, and I would bet my house on that formula because that formula has been numerically verified on thousands of points. And I can tell you that writing down the formula in a closed form fashion would take several pages of LaTeX. I can just tell you that the solution of the rates is the solution of a moderate degree polynomial, and I know it's the truth, but I cannot prove it, right? And it's a good question whether sometimes in optimization we need to have the proof, because it's at the end of the day we care about understanding the behavior of the algorithm. If I have something that I believe in just as much as any physics law, like Newton principles, maybe it's not proved, maybe it's fair enough, right? And so this is something that maybe we can touch upon. Okay, so that's the point where normally you believe I'm going to be a hero, making step 2 automatic. I'm going to have disclaimers immediately saying that it's not always going to work. We're going to be able to tackle simple situations. We'll have proofs of concepts that I believe are of interest. Also saying that I'm certainly not the first one to phrase things like that and to try to have things that are precise in step 2. Many people have tried to see for algorithms both an upper bound and counterexamples or lower bounds. Obviously, that's something that we all strive to do. Not everyone uses the same technique though. And obviously, it also doesn't solve everything. What I'm talking about is for optimization. This is all the subpart of federated learning, which is federated optimization. And people have talked about that. There is a striking difference between the two. It's not because we understand federated optimization that we know everything about federated learning. Great. OK, that was starting point. I'm going to be able to slow down once we get into the technique. Now, how do we do that? We build on the third bit of context, which is performance estimation. So who here knows about performance estimation by show of hands? OK, online. OK, thanks, guys. No, it's so performance estimation dates back from 10 years ago. It was introduced by Yoel Drori and Mark Teboul in 2014. It was then made more popular from 2014 to 2017, especially by the PhD of Adrien Taylor. And it was made even more accessible by the work of our PhD students that we supervised with Adrien Taylor, who's named Baptiste Gougeot, and who did a ton of work, especially on, I would say, making Python code on those aspects. So the takeaway from performance estimation is simple. It says that for most first-order algorithms, for most simple class of functions that you may think about, we can get the tightest convergence rate numerically in a few lines. Okay, and examples of that are given in the docs. Okay, so this is the documentation of that PEPIT package, performance estimation in Python. We have now more, I think, than 80 examples that are pre-implemented. For any of those, if you click on the link, you are going to get a program which is typically less than 30 lines that gives you the numerical guarantee, which is the best guarantee you can get on a particular class of functions. And I will even show you at the end some kind of user interface that enables you to explore that without even trying to type any Python line. Okay, and so what are the limits of that? The main limit is that it's mostly numerical. And at the beginning, what we want as mathematicians is analytical. And I'm going to show you how we could go beyond numerical. That's going to be one big part of the talk. And the second limit of that is that it typically takes 2 hours to introduce. And I'm given have about 30 minutes left, which means that I cannot really give you all the details. I'm going to give you a crash course that hopefully is self-contained. And if you follow me on basically 2 big slides, you will understand something normally if you don't know about performance estimation on how we obtain those numerical guarantees. Great. Okay, so what did we do? This is at the end, this is slide 1 in some sense. What we did was to look at a class of methods that many of you have contributed to, which is the class of error feedback techniques. So error feedback were introduced first, at least in the FL community, we often refer to the early 2010 years, and they have been reintroduced afterwards under many variants. And we placed ourselves in a very simple setup, which is basically contractive compression operators. So error feedback are used for communication constrained environments. And we took a simple setup and we compared basically 3 algorithms in the first paper, then in the second paper, 1 more. The first one is compressed gradient descent, the second one is error feedback, and the third one is error feedback 21, introduced by the team of Peter in 2021. That's the first part. The second part is how we did it, and that's, I think, maybe the most insightful part for you, because you guys already typically know about those algorithms. We numerically search for optimal rates of convergence but also optimal Lyapunov functions, because it's challenging to know, when we do optimization, you typically use Lyapunov functions. I'm going to re-explain what those are. But finding the correct one and the best one is not easy, and it happens that extending the framework of simple performance estimation enables to find optimal Lyapunovs. So we got numerical results, and then we did what I call engineering to actually transform that into analytical results. And I'm going to show you some of the tricks we used. And I want to say that it's not going to, for the moment, it's not fully automatic. There are a bag of tricks that you need to master in order to actually be able to do that. And the two parts, I believe, are just as exactly as interesting. The first one is really for people into the theory of federated optimization. The second one is for any people interested in optimization and doing proofs once in a while, and even beyond that. Because I think, okay, let's stop for a minute. That performance estimation approach has been something that is around for the last 12 years, and for me is one of the big game changers of the optimization community, especially the first order optimization community. So I think that's someone that everyone should be aware of. And again, I'm not the first one to contribute to that. I mean, the line of work really started 10 years ago, and I think Adrien Taylor has been the one contributing the most to that field. Okay, and for today, I'm mostly going to talk about that because, as I promised, I want to give you that crash course on performance estimation. So here we go. I'm going to stop for 30 seconds just to make sure that if there are any questions, I can take one question now, but it's going to be the most difficult slide, so maybe I take questions at the end of that slide. Yes, go ahead.
So is your technology primarily focused on proving convergence for stuff? Because the world of proofs is quite diverse. You got like techniques, proof by contradiction, proof by construction, all this type of stuff.
Yeah. Okay, so here it's going to be very easy in the sense that the proof that I'm going to be looking at is not going to be, in some sense, a mathematical complex proof. Just like what we do when we do mathematical Olympiads, we have to find proof techniques. Here the proof is going to be about finding the best possible guarantee. So maybe at the end of the slide, maybe you understand a bit better what I mean by obtaining proofs automatically. There are a couple of, at the first line, I'm going to obtain rates automatically and tightest rates automatically. There are going to be numbers that are obtained, so which is much simpler to obtain than a proof. Okay, so let's get into it. What is performance estimation? Performance estimation is that following thing. I want to, basically, I'm going to rethink the way we do first order optimization proofs. And typically what we do in first order optimization and in most optimization are universal guarantees. So what we say is that we want that for any setup in a class of setups, we can say something. And this is what we do in DP, this is what we do in robust learning. For any particular configurations under assumptions, we have something. So it's always some kind of worst case. People don't like the word worst case because it feels pessimistic, but any for all statement is a worst case statement somehow. And typically a worst case statement that we want is for any function within a class, let's say the class of L smooth and mu strong convex functions. Let's say I consider gradient descent, so you recognize W1 equals W0 minus a step size of 1 over L, the gradient of f at W0. I want that W1 minus W star squared, W star being the optimal point, is smaller than the contraction rate times W0 minus W star squared. Right, this is very fair, and basically I'm looking for guarantees stored here. I'm going to say that the best possible guarantee that you can get can be expressed as an optimization problem. So at that point, I'm doing just meta optimization. I'm saying that the rate I want to get in optimization is itself an optimization problem. It's the worst case for any function, any starting point of my ratio between my initial condition, W0 minus W star squared, and my objective metric, W1 minus W star squared. For any function within my class, the point obtained by gradient descent, and W star being the optimal point. And I can introduce those two variables, two variables, W1 and W star, as slack variables. And now all those things are just constraints. I have the constraint that f is in f mu L, W1 is gradient descent from W0, W star is the argument of f. And at that point, this is a bad problem, because it's an infinite dimensional set, right? This is infinite dimensional. There is no reason that it will be less than that. And this is certainly not convex. So we're in trouble at that point. Now I'm going to do a couple of simplifications of that. The first one I'm going to do is introduce G0, which is the gradient of f at W0, as a slack variable. Again, I haven't done anything. G0 is uniquely defined from f. I can just replace the gradient of f at W0 here by G0, and everything is just the same. The second modification I can do concerns W star. W star here I can use some kind of invariance by translation just to put it at 0. And so W star is 0. I simplify a little bit the expression I have. And the third bit I have is some kind of homogeneity. So for those who are used to optimization, typically, whenever I have a trajectory for a function in the class, I can obtain the scaled trajectory where everything is scaled up. All the iterates distance, the function is scaled up, etc., meaning that I can just assume that my denominator here is actually just 1. And that removes the denominator. Great. So at that point, I still have a problem which is pathologic, but a little bit less complex. Yes, go ahead.
Did all those operations preserve the isometric behavior of the optimization problem?
What do you mean isometric?
So you replaced like when W star was 0 and the other things.
Yes, none of that changes anything to the problem. I mean, basically, saying I look at the worst case functions and worst case behavior doesn't really depend on W star. So placing W star at 0 doesn't change that, for example. And I could actually not have used that thing. We can do it or not do it. It's just simplify a little bit the expression at the end, but I could do it without that constraint. Or actually, the same one, this one I could relax at the very end if I prefer. Now, we get to the interesting bits. The biggest problem I have in that optimization problem is the class of functions. This is infinite dimensional. But the good thing is that I actually don't care about the functions. Two functions that have the same gradient G0 at W0 would give me the same first point. So if I think about two different functions that have the same optimal point, same gradient at the initial point, they have the same behavior in terms of that metric. So in some sense, you can feel that I can actually quotient the space of smooth and strongly convex functions by the fact that two functions would be equivalent if they have the same gradients at the same point. I don't need to do quotient space. I can just say, actually, that what I'm going to do is remove the worst case over the function here. I'm going to only keep a worst case over the gradient at the initial point under the condition that there exists a function that has that particular gradient. Okay, and now I'm going to claim that this condition, the existence of a function, is something I'm going to be able to deal with easily, whereas the optimization of the class of functions was much harder. And now the only question I have is, how can I characterize the existence of a function within a class that has particular gradients at particular points? And this is what we call, this is this condition here, does there exist a function f such that the function has particular values fi's and the function has particular gradients gi's at particular points wi's? And this is something, I should hide the answer here for the moment, this is something we call interpolation. Because does there exist a function that passes through particular points is what we have called interpolation in many regimes. In comparison to interpolation in machine learning, which is typically interpolation in terms of passing through points, here we want to pass through points plus gradients. And I'm going to convince you that interpolation on the set of convex functions is actually very easy, because does there exist a function that has particular gradients here? I have represented 3 points, 3 function values, and 3 gradients, and the gradients I have represented by representing actually the tangent line. Does there exist a function which is convex and that goes through those points with those tangents? Yes or no? Who believes there exists a function here, convex, that passes through that? Convex? Who believes there doesn't exist a function?
I can't tell between the green and purple.
Oh, okay, that's okay. That's like, the function just goes through the points with those gradients. What's the problem? Clearly, you cannot have that. The function would have to be above the tangent. That would be the tangent. This point would be below actually the tangent. So here we cannot have interpolation. If now I move a little bit that point below, the points are completely symmetric with respect to each other. Now I do have a function. This is actually this function, which is the supremum of all my tangent lines, and it indeed interpolates those 3 values.
And so smoothness is very bad.
Second?
The smoothness is going to be very bad.
The smoothness is not going to be very high. That's right. I can just corner things out here. So you're perfectly right. I should do things like that. But actually, because I just want these 3 points, I have a bit of margin here. Very good point, though. And so I'm saying at the end of the day, it has been known that there exists a function that interpolates, which is convex, if and only if the function is above the sampled tangents for any per ij. And this is great. This is not the class I'm interested in. I'm interested in mu strongly convex and L smooth functions. But by working by transformations, I can actually get interpolation conditions also on the class f mu1. And the idea is that the function is strongly convex if only if f minus mu quadratic is convex. So getting from interpolation on convex to strongly convex functions is easy. And going from smooth to strongly convex is just by Fenchel transform. If I know that the function has particular gradients at particular points with particular value, I know what the Fenchel transform has as value as particular points that are actually the gradients, and which values it has. So I can actually obtain, and this is the part I'm skipping, I can obtain what we call interpolation conditions on the class f nu L. And I'm saying that there exists a function which is mu strongly convex and L smooth that interpolates the points if and only if I have that inequality, which is a sampled version of what we call the co-coercivity inequality, right? It's the most complex and most tight inequality you can get. And if you satisfy that, which is just a quadratic form of gi, wi, wj's, and a linear form of fi and fj for any pair ij, then just by seeing the gradients, you can obtain a function that passes through those points. Good. So at that point, the one thing I've said is that I can restrict my problem to the worst case over starting points w0, w1, and g0 under conditions on w0, g0, g star, wi, wj. And here I have simplified things a little bit with respect to the previous inequality. I cheated a little bit by doing the symmetric version of that. The reason why I can do that is actually here the function values don't matter, so I'm allowed to basically use the symmetric version of the inequality, but it's just to actually simplify the writing in the next few slides. So here, there's a little caveat in what I'm doing. If you look at the slides again one day, this requires an argument, but this is the same kind of inequality. This is the symmetric co-coercivity for mu strongly convex and L smooth functions. Great, and now we're done. This is exactly the same shape. This is the same equation as the one on the slide before. And I'm going to say that now this is very close to being convex. And the way I get a convex problem is by SDP lifting. I'm going to introduce the gram matrix of all iterates, all gradients. This is a matrix here of the gram matrix of W0, W1, and G0. This is a 3x3 symmetric semi-infinite matrix. And everything I've written is linear with respect to G. So my metric is just the second coefficient here. My initial condition is the first top left coefficient, being 1. My inequalities linked to the function class are just linear functions of G. And my algorithmic constraints can just rewrite that as the square norm of the difference being 0. And again, this is a linear function of G. So now I have a problem which is the worst case second coefficient 2, 2 of a positive semi-definite matrix under a list of linear constraints on G. And this is called an SDP, and this is something you can solve numerically. And this is something that everything I have done can be applied to a much wider class of algorithms. Basically, anything which is first order, any class of functions on which you can interpolate. So basically, a functional class, an algorithmic class, a worst case guarantee. I can rewrite the worst case guarantee as the worst case function initial point and sequence of points that I have generated. I'm going to do exactly the same steps. Sampling in order to go from infinite dimensional to finite dimension. Interpolation conditions to characterize the existence of a function that within the class that has those particular gradients, and SDP lifting, and I get that my worst case rate of convergence is just the worst case value of a linear form of G under G positive semi-definite and a list of linear constraints.
Just one.
Yes, that's the moment to ask questions.
So just so I understand, so anything we can write as like first order constraints, like that supporting hyperplane interpretation or the co-coercivity thing you wrote can be done this way. But is there a way to also do things like self-concordance or quasi-self-concordance?
Exactly, it's a very, very good question. How far can we go? Typically, the simple thing that we can do is most first-order methods. You can do line search, you can do span search, you can do some kind of mirror descent. Those things you can do. Whenever you go higher order, right, it's more complicated.
So if my algorithm is, let's say, first order, but I'm analyzing logistic regressions, yep, I just want the class to have, let's say, self-concordance. Is it possible to do that?
Not directly, but this is, there are many, many extensions, many things that you can try to tackle with more work. Okay. And so the short answer is that. Yes, go ahead.
So this is very nice, very clean introduction to this performance estimation technique. I have two questions.
Sure.
So first, here you are trying to estimate the one-step performance.
Yeah.
What if I want to do multiple steps?
You can do multiple steps.
The dimension of G would blow up like quadratically.
The dimension of the G matrix.
Linearly.
The dimension of the SDP would increase because here, basically, I will have to stack all the gradients I've seen. And indeed, for some problems, the dimensionality of the SDP is a problem. What I can show you is that we can easily analyze problem, 10 steps or 20 steps, but typically we don't want to analyze 20 steps. We want to analyze 1 step or 5 steps and guess the closed form formula mathematically and afterwards go back to mathematics. But we can show you, I'm happy to discuss more examples on that. It's a very good question.
Okay. And another question,
Yeah.
Here the algorithm is completely given, even including the hyperparameter, like the step
Yes,
size.
yes.
What if I want to estimate the optimal step size?
This is a very good question. What you can do is just like run numerically and try to guess what the optimal step size is.
And then run another optimization over.
And sometimes you can add the step size in the optimization problem,
Yeah,
and you can show that. Basically you can optimize for the step size. I'm going to show you how you can optimize for the Lyapunov in a few minutes. But sometimes you can optimize for the step size. Otherwise, you have to rely on like exploration and then trying to make deductions.
It's like backtracking line search or something like that can be added as a constraint.
You can add also plenty of things like that. Yeah, sure.
Yeah, because for gradient descent, there is a known method, silver step size. Can
Oh yeah,
accelerate.
this is more complicated, but yeah, this is.
Will this method enable us to discover silver step size if we optimize?
To some extent, yes. Typically, if you try to find the best sequence of 2-3 step sizes for gradient descent, you can approach that with that. And this is actually the first way it was approached. Anyways, so finding a worst case, the takeaway number one that you need to take away is finding a worst case guarantee can be cast as a convex problem. We can automatically obtain worst case guarantees numerically. It's very helpful for design of methods and proof checking. It's all numerical. And typically, we can have different metrics on both sides, which doesn't help to basically iterate that among many iterations. And it means that typically from that thing, if I have different metrics, I cannot get a rate for multiple iterations. So to get that, typically we're going to be interested in Lyapunov functions, and the Lyapunov function has the following characteristics. It's good. Typically, a Lyapunov function is something that when it goes to 0, my point has to go to the optimal point. And typically, you can think of Lyapunov functions that are just like the square norm is a Lyapunov function, but let's say the function values plus the gradient norm would be a Lyapunov, and any combination of the state variables that you want to do, which would enable you to get a proof. Okay? And the typical things that you want is that it's non-negative and that it's 0 only at the fixed point. And if it's upper bounded, I can have an upper bound on the square distance, say, to the optimal. Okay? And finally, the main property you want is that it decreases at a linear rate. So after one iterations, xi1 here and xi0 correspond to state variables that describe the state of the algorithms beyond the position of the algorithm. That's the state and that's the position. I want such a contraction to be valid at any iterates. And if I have that, obviously, for any states xi0, x0, then I have that for any number of iterations, and I'm happy. So now, this is the second big chunk of performance estimation. The first one was the first hour. This is the second hour that I'm going to do in 5 minutes. Again, I'm asking a lot from you, but hopefully you can stay with me again. I'm going to say that the worst case rate for Lyapunov can be written that way. This is what I've done before. And I can write that, as I've said, as a primal problem, which is an SDP under a list of constraints. And here, any feasible point, meaning any G that satisfies those things, means any gram matrix for which I can recover a sequence of points in a particular dimension and a function, which is within my class, such that the iterates are the iterates obtained by the algorithms on that function. So basically, any primal feasible point here corresponds to the value of the rate I would get on a specific function. So that's a lower bound on the rate. Any counterexample gives me something I cannot do better than that, lower bound on the optimal rate. Now I can go to the dual, and the dual corresponds to introducing one multiplier per linear inequality. There's one multiplier for the initial condition, one multiplier for each constraint, coming either from algorithms or for the class. And my dual writes as the infimum of the tau here, which is one of those variables, under the constraint that basically my performance matrix minus tau, the initial matrix, minus the sum of lambda k and k's is smaller than 0. And now what I can say is that any dual feasible point gives me an upper bound on the rate. Basically, any value here of lambda and tau such that this is valid gives me a number, and that number is going to be higher than the optimal rate. And actually, I'm even claiming that getting the values of the lambda k's, that inequality is exactly the proof of the convergence of the algorithm that I require. So basically, that dual variables is actually what we call a sample proof. And if I get the values of the dual variable, I get the proof. And finally, again, here I'm doing a ton, but I hope that you get at least the high-level ideas. A rate is valid, so it can be achieved, if only if I have that feasibility problems over lambda, does there exist lambda such that. So that rate is correct for algorithms if and only I have that. What I'm doing here is that I'm going to start trying to optimize over Lyapunov functions over the validity of the rate. So finding the best Lyapunov functions is equivalent to saying that I want to find the optimal Lyapunov that minimizes the rate. And here I have to do a bit of linear parameterization. So I'm going to say that basically, let me show you an example first. They're going to be a bit easier. Let me say that I have the gram matrix of all my iterates and all my gradients. This is the state at the initial point. This is the state after one step. And I'm going to say that the typical Lyapunov could be any linear combination of x1 minus x star and g1 squared, which corresponds to a linear form of the second block of the gram matrix. And that linear form right here, I could use any actually matrix of size 2 by 2. We're going to search for those matrices afterwards. Those are the matrices whose number I want to obtain. I mean, getting that thing is equivalent. If I want to write that as that, I can just rewrite basically the subselection of the lower block as that matrix product times the matrix P, which is exactly equivalent to the trace of A1G, A1P, which is the same as G times the performance metric. And here you just see that I'm able to parameterize my performance metric linearly with respect to G, with A1 being those simplic matrices that select the last part. And for the initial part, for the Lyapunov at iteration 0, this is the same thing. The only thing I have to change are the A0 matrices that select the first coefficients of G. This is the part normally where I should have lost you a little bit, but that's okay, right? It's the part I know I'm being very quick because I just want to somehow convince you that I can linearly parameterize mperf and minit with respect to P, which means that now there exists a matrix P for which the rate tau is feasible if and only if I have the feasibility problem over P and lambda simultaneously, which is the following problem. I have just replaced mperf and minit by the version linearly parameterized by P, and now have a feasibility problem jointly over P and lambda, and the magic of that is that this is actually still convex. So I'm claiming that searching for Lyapunov function that satisfies a particular rate, so searching for a particular Lyapunov function for which there exists lambda such that this inequality is valid, is convex. And it's not jointly convex between the rates rho and P. So that's a problem. So actually, it's not jointly convex. In order to find the optimal rate, we're going to have to do bisection. We're going to try rates, and for any rho, this is going to be a convex problem, and we're going to converge towards the optimal rho.
So
Yes?
I have a question. So in a way, like if you take like a basic guarantee for an algorithm, one that is like based on theory, right?
Yes.
You would have like possibly a loose performance.
Yes.
Right? And when you do this automatic
Yeah.
performance estimation, in a way, if you have something that is slightly better than the basic guarantee, you're already quite happy.
Yep.
So why don't you focus on like the relative tightness of your Lyapunov function compared to the basic guarantee?
Because, I mean, okay, it's a very good thing. It's typically I could try to see how much I gain. I'm just going to try to, okay, I mean, you say that I could just use that for guarantees that exist in order to find if I can improve them?
So to this problem, you could normalize with respect to the guarantee. You
Yeah.
have like just by taking a constant Lipschitz function, Lipschitz constant, and so on.
Yeah.
And then just do a few steps of your optimization. And
Yeah.
It's already better than.
Yeah, I mean, I'm going to claim that I get even more here, in some sense. I'm going to get the best guarantees and sometimes things that look nice. Okay, so let's take it offline because I want to get to do the federated learning algorithms. So we can look for optimal Lyapunov and optimal step size, optimal rates. And here, okay, I have to stop for a moment to explain how we apply that huge hammer to those error feedback algorithms. So I would say this is the part I'm going to be quick on, but I feel like I'm already quick on everything, so maybe it's an overstatement, right? But we're doing distributed optimization. This is something you know about. I can do gradient descent. There's a communication bottleneck. I can do compressed gradient descent, typically with the compressor being top one or quantization operator. This is problematic. This is an algorithm which is called compressed gradient descent. I may want to improve that, and there are two ways of improving that. I'm just going to cover the first one, which is called the error feedback technique. The principle of error feedback is whatever mistake I've made in the past, I'm going to correct and keep a memory of and correct in the future. So I do my method, which is my compression. I look at the error I've made, I keep that in memory, and next time I want to send a gradient, I add my memory term, and I have a message. My new error is the difference between what I wanted to send and what I've sent. In error feedback, only the sender has access to that control variate EIK. Okay, that's the iteration. The only thing you need to remember from that is that there is a variable EI, which basically corresponds to the state of my memory. In error feedback 21, this is a little bit different. The spirit of error feedback 21 is whatever we both know, I'm the sender, she is the receiver, whatever we both know, we're going to subtract before sending. So here, before compressing my gradient, I remove a variable that both the sender and the receiver have access to. And after that, when I do my update, I add to the message that shared variable. And I have a way to updating that too. Those two algorithms, basically are created in order to reduce the impact of compression on those compressed gradient descent type algorithms. Okay, they're different spirits, but in a paper by Peter, I think actually the first paper, it's shown that they can be linked in the case of linear operators. But in spirits and in the way they function, they are not the same. And the rates given are typically not the same. There is a huge literature on that, and many rates. Not all of them are comparable. Many of them provide insights. They show in which situations it failed, what it enabled to unlock. But what we were looking for is actually just a tight theory, rates that enable to compare everything in the most clean fashion, and leveraging those performance estimation techniques. And the second thing you need to, so the first thing you need to remember from those 3 slides is that the state variable of my algorithm is going to be encoded by that decay. It's going to appear in the future. And I have that parameter which characterizes the compression, which is at epsilon, right? And that's an epsilon of 1 means that I can allow my compression to be 0, so I have no more information that flows. And an epsilon of 0 means that my compressor is identity. Okay, so now let's go and try to compute our optimal Lyapunov functions. My state variable is what I've just said. It has the points, the gradients, and the memory term. This is my state variable for EF21. And here, let's go and do what I've done. So I take eta, which is a step size of 0.3. I take epsilon, which is my compression factor of 0.1. And I obtain the following optimal Lyapunov function. And there, as my PhD student Daniel, who is the main contributor of that, would say, this is a Lyapunov function that we deeply care about, but that unfortunately looks bad, right? So it's not something I can directly exploit. So it's not even unique. So we're going to have to do tricks in order to get to something we can exploit. The first thing I'm going to do is say, oh, many of the coefficients, those top left and top row coefficients are actually close to 0. Let's just drop them. And afterwards, I'll typically force that the rank is, sorry, the trace is 1. So this is just 1 minus the other one. And those two coefficients look very close to minus this one. So let's just assume that the shape of my Lyapunov function is actually that. I'm restricting the set of possible Lyapunovs. And then I compute the values of P33, depending on epsilon. I get something like that, which starts to look like something maybe that I can exploit. I'm going to go further. I'm going to say that instead of trying to find a feasible point of that with my rates, I'm going to try to find the solution that has the minimal rank. Rank heuristics typically tend to force the solution to be pushed in the same corner. Rank is actually very bad because it's non-continuous. So what we're going to do is we're going to just take a relaxation of the rank. So typically the log depth relaxation could be good. And now I'm going to basically claim that this thing, I can find a way to solve that iteratively. Okay, I'm going to just skip the basically slide on which I explain how to do that. And if I solve that iteratively, it's, iterative linear approximation, I'm going to get those values for P33. So this is now the value of the coefficient that parameterizes my Lyapunov that is enough to obtain my optimal rate of convergence. And now I'm going to go to symbolic regression. I'm going to feed those values to symbolic regression. And there are plenty of excellent symbolic regression packages. And I'm going to obtain that there is a perfect one-to-one match between the values that I've obtained numerically and 1 over 2 plus square root of epsilon. And I'm claiming that at that point, we knew we had found, most likely, the valid shape of the optimal Lyapunov for EF and EF21. And that's it. We arrived at a proposed closed form formula for the best possible Lyapunov of the class, both for EF and EF21. Those two Lyapunovs are not the same. They have no reason to be. They don't even have the same shapes. One is based on the gradients. The other one is based on the iterates. It's kind of a duality between the two. And we had combined the primal point of view, the dual, the best Lyapunov search, guessing numerically which coefficients are 0, rank proxy, symbolic regression, and all those ingredients. Okay? And now I'm going to, do I have 3-4 minutes? Okay. I'm going to show you how we can do that in a UI. Okay, so basically we have that UI. If you want the link, I can provide it. It's under development, but it's something you can already use. Typically, you can choose algorithms. So here I'm going to choose EF. If you wanted to do your own algorithm, you could just customize it. I do EF. I get that very long algorithm. Okay, but we can have a look. Most of it is straightforward. It's Python. It's easy to understand. And typically here, I see that I have my gradients that are defined. Here I'm adding my memory term. Here I'm doing the compression. Interestingly, the one thing I needed to do that was that the compression condition C of x minus x squared, this is smaller than epsilon times x squared. This is again something which is linear with respect to the Gram matrix. The reason why we could use those assumptions, the reason why we use assumptions that are homogeneous is that typically, they are the ones that work well in the proof. So this is how I encode that. I have my compression, which is satisfying my assumption. And then afterwards, I'm going to do my steps. This is my compression. I do my gradient descent step with my compressed message. So this is exactly EF. Great. Now I'm able to, this is here I'm defining the optimal Lyapunov that I've obtained. Obviously, at the beginning, we didn't know the Lyapunov, so we played with that in order to find the Lyapunov. But if I know the Lyapunov, I can afterwards set here the maximum. This is epsilon min, epsilon max. What is called gamma here is the compression rate. The number of iterations I want to look at, I can do 10 iterations if I want. I can select the function class that I want, smooth, strong, and convex. I'm going to take mu of dot 1, L of 1. And I can click on the plot button here, and this is going to give me the following thing. This is going to give me the rates, and this runs in 5 seconds, right? It's going to give me the rate for any epsilon, any n of error feedback with the Lyapunov that I've done. I can now enter, if I want, the formula that I've obtained in order to check. I enter the very complex formula. This gives me the orange curve. Look at the difference. Before it was gray, now it's orange. It means that there is a perfect one-to-one match between the formula that we have obtained in theory and the one which is predicted. Same with respect to n. And obviously, that works for any n and epsilon combination. So this is really something that enables you to try to play that game of guessing the rates, comparing methods, etc. More interestingly, you can now look at the dual values. The dual values are the values of the multipliers that you need in a proof to have a proof that works. You can just select all dual variables that are associated to any pair of points, and I can plot those dual variables. I obtain those plots, again, with respect to epsilon. And what I can do here is say, OK, those two values look very small. And if you look at the values, they're actually much smaller. So this one is very small. This one is kind of small. Let me resolve the SDB problem by removing those. So I can click. Oops, I click on both. And I can click on recompute here. And I'm going to recompute the guarantee without using some of the inequalities that I could use in the proof. And what I'm going to obtain is that now green curve. So I'm sorry if some people can't see the difference. The truth is that the green curve is exactly on top of the orange curve. So I can't do much. So it says that without using those two inequalities that I believed wouldn't exactly the same rate. And you can see how this enables to really explore basically the set of methods that we can run. Because I'm able to play with inequalities in order to know before trying to do the proof if those inequalities should be used or not in the proof. Okay, so this is, I guess, the conclusion slides. We used advanced computer-aided proof techniques. We obtained results that I haven't talked about on performance on error feedback and error feedback 21. In the first paper, we limited ourselves to the single agent case, which is surprising because it's non-distributed distributed optimization. It was already very challenging, and it does make sense. It's a context in which I'm the only one able to create the gradients, and Kshitish is the only one able to make updates, and we have to communicate with limited bandwidths. And so in that case, we showed that basically EF and EF21 had different Lyapunovs, but exactly the same worst case rates on smooth and strongly connected functions, which was unknown to our belief, and that they were both dominated by compressed gradient descent, which doesn't even have that error feedback mechanism. And we recently released the version in the multi-agent case, which is much more complex. In some situations of the multi-agent case, you have that, basically heterogeneity makes you fail. So we have different types of regularity that we tackle, either heterogeneity that we tackle, either statistical heterogeneity, so having different optimal points, or regularity heterogeneity, a case in which I don't have the same ui and li as the other agents. And in some situations, we have theorems. In other situations, as I said in the introduction, we just have empirical laws, meaning that we have formula that are not closed form formula, typically roots of polynomials that exactly match numerically the truths that we obtain. and we just believe it's a law of nature. It's not something we can prove for the moment. We don't believe anyone can prove that. Maybe a computer, considering the length of the proof, it's extremely, considering the length of the expression, if I had to write it down. And we believe to some extent, maybe in some situations, this is something that is enough. The tools, I believe, are very versatile, and I hope more people are going to try to use those tools, especially for exploration and contributes. It's meant to be very collaborative, so whenever you have an algorithm, add it to the set of examples in Pepit, and this is something that then is going to gain momentum. And we believe those things can help basically advance and clarify the field, which is very complex. And to complement that, this is, I promise, the last slide, what we do is to say that, okay, this is great. We now have rates that are tight, but the typical expression that you get is this one, right? So this is the optimal rate that I didn't want to show, and it's not because it's tight. I believe that in some sense, if we believe that there should be some knowledge to be learned from a rate, then we should have more knowledge from the tightest rate, because otherwise it just means we have a non-precise guarantee on the behavior of our algorithm. So I believe this rate it's good to have the tightest rate, but it's kind of complex to look at. It means that the proofs are not always going to be easier to check. So what we do is basically to say that, in the papers that we write in that line of work, we support all the results that we provide with numerical and computer algebra systems certificates. Meaning that basically, when you have those two blocks here, and you can click on those, and if you click on the performance estimation block, you are sent on a IPython notebook on which you have our guarantee, which is written in LaTeX, and our algorithm, which is run, and the guarantee computed in Python, and you see that there is this perfect one-to-one match. And maybe now you don't need to review my paper just as much, because at least you believe that there is some kind of numerical evidence that it's true. But if you don't trust me anymore, you can click on the other link. This is a computer algebra system, so this is a Mathematica script, which basically does our proof and verify that what we have written in the proof is at least Mathematica level correct. This is not formal mathematics yet. It doesn't replace the proof. The proof is given in the paper. We believe proofs are great. But in some sense, so this is the Mathematica notebook. Feel free to check it out. And ultimately, obviously, we want to go towards formal proofs, lean language or something like that. This is still complex to do. But at the beginning, we have something that can help in the review process and maybe help us identify the parts where we need to focus on and the parts on which we want to spend less energy on. And for me, the part we want to focus on again is step one, is inventing new assumptions that make sense to quantify heterogeneity and having them match what happens in practice, and not doing the proofs and verifying those proofs, because this is technical work and hard to do, and the people that do that have a lot of merit. Okay, and this is actually the end. I'm happy to talk more about those things. Although the week is almost over, there is a chance I will be back in a couple of weeks, and otherwise, feel free to send us an email, and we're going to keep working on those things. So we're very excited to collaborate on those. We can take questions or decide to take it offline, because I went a bit over time.
Let's take the questions offline and also take a 5-minute break, so you guys can have time with Aymeric. But we have some break before the open prop session. But I want to thank Aymeric again for a wonderful tutorial on techniques for those of us who don't know much about them. And yeah, okay. Coming back at 2. So one place where I think I kind of missed is when you linearize the class using this P, you don't lose anything on the primal and dual certificate, right? Or you do?
No, I don't.
So what does linearization cost you? So
the linearization